Hi there, my name is Conway Nelson. I'm the Vice President of Project Development and Technical Services here at the International Carbon Capture and Storage Knowledge Center. I'm pleased to be part of the CarbonExpo webinar today, and I'm going to talk to you a little bit about the Knowledge Center itself, our foundations, which are rooted in the Boundary Dam Unit 3 project in Estevan, Saskatchewan, Canada, how we've used the lessons that we've learned and the knowledge we've gained from that project to aid people in other industries as they're embarking down a path of looking at carbon capture and storage projects. So who is the CCS Knowledge Center? We're a nonprofit organization. We were started up in 2016, about a year or so after the initial operation of the Boundary Dam Unit 3 facility, with the goal to really accelerate the global deployment of carbon capture and storage projects. We're unique in this space in that we have experts on our team that are involved in the development, the construction and execution, and the ongoing day-to-day, even currently, optimization of the Boundary Dam Unit 3 facility. We're really here to share the lessons that we've learned, the knowledge that we've gained with people in other industries that are also looking at CCS projects. The lessons learned from this first-of-a-kind project are highly applicable across all different industries, and I'll talk a little bit more about that. And really our goal is, again, to accelerate the deployment of CCS projects and provide people with advice that'll lower their costs, reduce their risk, and improve the performance of their projects. So this is an overview of the Boundary Dam Unit 3 power plant and carbon capture and storage facility. Just to orient a little bit, so the power plant is here. There are 4 existing coal-fired power plants that are in operation. 2 actually have retired, so it was originally a 6-unit plant. The carbon capture facility is here, the compression building, the carbon capture equipment, and the heat rejection equipment, the cooling towers are out in this area over here. So the carbon capture equipment does take up a rather large footprint. These are major projects, major undertaking for companies, which is why we feel it's very important for us to share what we learned through going through this exercise as one of the first in the world, so that other people can not repeat some of the issues that occurred on the BD3 project. The BD3 project has achieved its design capture rate of 90% of all of the flue gas that goes through the capture plant. It's the world's first fully integrated post-combustion CCS facility on a coal-fired power plant. And as of the end of 2022, it's achieved 5 million tons of CO2 captured and stored. So a little bit of background on the Boundary Dam Unit 3 project itself. SaskPower elected to life extend an existing 45-year-old asset, the Unit 3 at the Boundary Dam Power Station. This unit was nearing the end of its useful life. Useful life for a coal-fired power plant is typically around 50 years. So there was a decision point coming for this unit whether SaskPower would re-inject money into it and life extend it and continue to operate unabated, or add carbon capture to it, or source another type of generation and simply retire the unit. At the time the decision was made, there was not yet a carbon tax in place in Canada. However, there had been a lot of conversation about regulations coming to limit the use of unabated coal-fired power generation. And through these conversations, by the time the decision was made to proceed with the capture plant portion of the Boundary Dam Unit 3 project, regulations were enshrined and they were in place. At the time that the decision was made, this project was actually cost competitive with natural gas combined cycle, without a carbon tax, without any sort of other economic tool that would sort of level the playing field. If you'll remember back though, 2009, 2010, in that time frame, the price of natural gas was quite high. It fluctuated between $5 and $10 per gigajoule, which is a lot higher than it is today and a lot higher than it was shortly after Boundary Dam Unit 3 went into service. But at the time of the decision making, those were the economic projections that were in place. So for the project itself, the total capital expenditure was about $1.5 billion. This was aided by about a $250 million grant from the federal government, and it was executed in 2 parts. So there was a power plant upgrade, the life extension of the existing power plant. There was a new steam turbine installed. There was a new boiler installed. Essentially, the boiler was life extended and made to produce slightly higher temperature steam and more steam to be a little bit more efficient. And then there was the carbon capture facility addition. And the cost of the carbon capture facility addition was about $900 million. And that came in 4% over the original budget. So really, for the first of a kind project in the world and a mega project like this, we're quite pleased with where the capital cost came in on the carbon capture side of the project. The development phase of the project started in about 2007. There was a quite detailed FEED study executed, which led to a final investment decision for the power plant in late 2010, and a final investment decision for the capture plant in early 2011. Now, I say it was an in-depth FEED study because by the end of the FEED study, SaskPower actually had executable contracts in place for about 2/3 of the capital cost of the project. So a lot more certainty than you might see in some other projects, but it felt that was necessary, being this was a first of a kind project in the world to fully integrate a carbon capture facility with a coal-fired power plant. So once the investment decisions were made, the construction occurred and the capture operations began in October of 2014. Another economic driver behind the BD3 project was the use of the CO2 for enhanced oil recovery. Using the captured CO2 for EOR is a proven method for rejuvenating the production of mature oil fields while also providing safe permanent storage of CO2 in deep geological reservoirs. 90% of the CO2 emissions from the Boundary Dam Unit 3 facility have been directed for commercial use in the long-established EOR operations in the Weyburn-Midale oil field, operated by Whitecap Resources. This field is about 50 kilometers from the Boundary Dam Power Station. It's the world's largest EOR project using anthropogenic or man-made CO2, and has safely sequestered more than 38 million tons of CO2, about 1.5 kilometers underground for the last 20 years. Years of scientific research has shown there's little to no release of CO2 from the Weyburn oil field. The other 10% of the CO2 has actually gone to the Aquastore well. This is a research well that was developed by SaskPower. It's owned by SaskPower and operated by the Regina-based Petroleum Technology Research Center. Aquastore is the most comprehensive full-scale geological field laboratory for CO2 storage in the world. It's demonstrating the scientific and economic feasibility of deep saline geological formation storage, and is providing the know-how for other jurisdictions and companies that are thinking of doing the same. Aquastore has been instrumental in demonstrating the safety and reliability of onshore saline aquifer storage. More than 500,000 tons have been sequestered to date, and no induced seismicity or leakage has been observed at Aquastore. The leakage has been confirmed using a combination of 3D modeling and 4D seismic to track the migration of the CO2 plume from the aquifer, which is 3.4 kilometers underground, so it's a very deep well. There's also an extensive suite of surface and subsurface monitoring and equipment in place to ensure that we know what's happened to the CO2 underground. One of the big challenges when people are considering adding carbon capture and storage downstream of an existing facility is energy. The amount of thermal energy in particular that's required to actually operate the amine process that's used to scrub out the CO2. In addition, there's a lot of energy required to actually compress the CO2 so it can be transported and safely stored. I'll walk through some of the highlights of the process here at the Boundary Dam Unit 3 facility. Basically start with a pile of coal, which gets ground down very fine and combusted in a boiler. The boiler is used to create steam. The steam runs a steam turbine, which isn't shown on the diagram. That produces electricity, and that's SaskPower's main product that goes to the people of the province. The other thing that the boiler produces is flue gas. Now, the flue gas is what we're dealing with the carbon capture facility. About 13% of the flue gas is actually carbon dioxide. And prior to the installation of the carbon capture facility, the flue gas was put through a dust collector to capture fly ash, and it was sent up an existing stack and emitted into the environment. So now with the carbon capture facility, there's a long duct that's installed to run over to initially an SO2 absorber. SO2 levels must be very low for the carbon capture amine process to work effectively, down to single-digit parts per million. And an amine scrubbing process was selected for the SO2 removal, and it actually allows SO2 to be removed in a form that's pure enough that it can be converted into hydrochloric acid and sold for some additional revenue to help offset the cost of the project. After the SO2 absorber, the flue gas goes through a CO2 removal process, consists of an absorber and a reboiler or a stripper. And this is where the bulk of the energy is required to regenerate the amine and keep this process moving. The other big energy energy requirement is this compressor right here. So once the CO2 comes out of the stripper, it's dehydrated and it's compressed down up to a pressure of about 2,500 psi or 170 bar. It's put into a pipeline and it heads off to either the enhanced oil recovery facility, which is here about 1.5 kilometers deep and producing additional oil and helping to improve the economics of oil recovery. Or in our case, SAS Power's case, about 10% of the flue gas can come, 10% of the CO2 can come over the AquaStore storage well, which is over 3 kilometers deep, and that's where the rest of the CO2 goes. Some of the interesting things that were done on the Boundary Dam Unit 3 project, and we like to call it a fully integrated project, in that there was an opportunity here for SAS Power as they were rebuilding the boiler and they were rebuilding the turbine. So the entire Rankine cycle used to create electricity was being redone. So they took the opportunity to increase the temperature of the steam coming out of the boiler, replace the steam turbine with a steam turbine that was custom designed to allow the capture facility to extract steam at just the right conditions without wasting some of that steam. It comes in at just the right place to actually minimize what's termed as the parasitic load to the capture plant, to the power plant, which is essentially how many megawatts of electricity that they lose. The other innovative thing that was done here was some thermal integration. So one of the things that has to happen to the flue gas before it can enter the capture facility is it needs to be cooled significantly. What we found going through the analysis is that the cooling that happens here on the diagram is actually very similar to the heating that's required to preheat the water for the boiler that's used to produce the steam. So those two systems were combined. There's some thermal integration done there, which helped to save in the order of 4 to 5 megawatts of power loss from the existing BU3 facility. The other piece of equipment here is another source of cooling. So there's a significant amount of cooling required in addition to the flue gas cooling. The amine heats up through the process over here. It needs to be cooled, and some other auxiliary systems. So the other major piece of equipment that's required for carbon capture project is a heat rejection plant, or typically a cooling tower. So the Boundary Dam Unit 3 project, as with any project, had a number of successes and a number of challenges. This is all to be expected with a project that was a first of its kind in the world. And I'll walk you through a few of the key successes and the key challenges. I could literally talk for hours, and our team does talk for hours with people that are considering carbon capture and storage projects about the long laundry list of lessons learned from the Boundary Dam Unit 3 project and how applicable they are to other industries that are considering carbon capture and storage. So I'll start with the success side. The carbon capture process itself was actually a 7,000-to-1 scale up. SAS Power's partner on this project was Shell Cansolv, and they had to scale up their process by 7,000-to-1. So a lot of risk mitigation efforts went into this prior to project final investment decision, and that really went off without a hitch. There were no issues with a scale up of that magnitude. So that's a big feather in the cap of the Boundary Dam Unit 3 team. The next one is thermal integration. So I'd mentioned some of the work that was done to minimize the lost electricity generation from the steam that's borrowed from the power generation Rankine cycle. And that was done quite effectively on Boundary Dam Unit 3. That's considered a major success. And again, there was an opportunity because all of the power generation equipment was being redesigned, but it was a major success for this project. One of the major risks going into the project was the flue gas cooler. So the flue gas, again, needs to be cooled before it enters the capture process. And the flue gas itself isn't the easiest thing to deal with. And as your temperatures get down low enough, the flue gas can actually condense liquid acids. And obviously acids are not going to work very well with a typical tube style heat exchanger. So a lot of risk mitigation went into this, again, prior to final investment decision. The project team traveled to go look at some flue gas coolers overseas in Thailand that had actually been put in service and had failed. And they ended up actually using a different design that had been tried in the past, and we went with Teflon tubes. So this is some of the failed tubing from the boneyard in Thailand, where the crew went and saw some old flue gas coolers, and we actually installed a Teflon material type tubes, and they've worked fantastic. There really haven't been any issues with that flue gas cooler, and it is felt to be one of the biggest risks going into the projects. Regulatory permitting. So there weren't regulations in place. Again, first of its kind in the world. Saskatchewan was already storing CO2 in the subsurface, but nobody was capturing carbon. Nobody knew what to do with some of the potential air emissions coming out, or some of the solid waste products that come out of the carbon capture process. So a lot of work was done to engage with the regulator, educate the regulator, in some cases actually go out and seek regulations in other jurisdictions that could be used in Saskatchewan to manage some of the air emissions that were potentially part of the carbon capture process. And that was successful. We were able to work with the regulator to get us a permit for the project upon commercial operation, and nothing has had to change in terms of the regulation. Everything was done properly, and the current system is what we're operating under today. One of the other key successes was transition to operations. So if you can imagine SaskPower's operators, they were very good at turning coal into steam and into electricity. They weren't really very good at managing chemical processes, which is really what this amine post-combustion process is. So it was a large diversification in terms of the skill set of SaskPower staff. And in order to facilitate transition operations to be the success that it was, a separate team was actually formed to manage the transition operations effort during construction. So another team was brought in, worked on training operators, building an operator training program, recruiting people. And one of the key components to the transition operation was the addition of a simulator. So SaskPower actually purchased a fully functional simulator that is still used today to train new operators and do continuing competence with existing operators. So those are some of the key successes from the Boundary Dam Unit 3 project. Some of the challenges. So the first three bullets on the challenge box, they really go together. The first one being particulate buildup. So when you burn coal, you produce fly ash. There's a dust collection system installed, an electrostatic precipitator, and the electrostatic precipitator will remove about 99.5% of the fly ash particles that are in the flue gas. The problem is that 0.5% that still gets through. Being that the amine system is really a closed loop, and the amine just circulates through the same equipment over and over again, this fly ash will build up. And it builds up to levels where it causes issues with fouling. As you can see in some of the photographs there, the fly ash does foul some of the equipment, which has made SaskPower change some of its maintenance plans, maintenance operations. Amine degradation, and this is still an issue that actually exists throughout the carbon capture industry using amine post-combustion. There are a number of different chemicals that can be present in flue gas that can compete with the carbon dioxide for reacting with the amine. And I won't get into the laundry list of things that can cause some of these degradation reactions, but just know that they are happening, and it is something that really needs to be considered. And that kind of fits into the third bullet, which is flue gas characterization. One of the things that we talk to very early on with clients that are considering carbon capture and storage is how well do you understand your flue gas? Do you know what's in your flue gas? Do you know how much it varies over time? If your fuel source maybe changes, it's not consistent. Most industries, they treat their flue gas, and rightfully so, as a waste stream. So they'll measure their flue gas really to the extent that they need to satisfy the regulator. What is changing when you consider carbon capture and storage is that flue gas is now an input to a chemical process. So you really need to know what's going into your chemical process so you can design the chemical process to withstand what's coming into it. You may need to look at different levels of pre-treatment to get the flue gas properly conditioned before it goes into the carbon capture process. So those three are kind of interrelated. The third piece is a reduced capacity. So the Boundary Dam Unit 3 facility was designed for a daily capture rate of about 3,200 tons per day, and which factors out to about 1 million tons per year. That's the design capacity of the system. And it's operated at a reduced capacity for most of its life, and I'll get into that a little bit more. And there are two key factors to this. One is fouling. So if you can imagine fly ash fouling in all of the absorber tower, packing system surfaces, heat exchanger surfaces, all this equipment, you're going to end up with some back pressure. You're going to have reduced capacity over time. So maintenance things have been changed to do cleaning more frequently to try to keep the capacity up, but there is a limitation there caused by that particulate buildup or that fly ash. There are also some economic factors. So as I mentioned previously, there was not a carbon tax in Canada when this unit first went into operation, and there wasn't a carbon tax for the first 6 or so years of operation. So the economics are changing a little bit. It is more economical now to work towards maximizing the capture of CO2 from the power plant. But prior to that, really the more important thing to SAS Power and its customers, particularly when power demand was high in the winter or in the summer, was to generate electricity. So there wasn't really a push to maximize the CO2 that was captured. The other challenge was the actual enhanced oil recovery agreement wasn't for the full amount of CO2 that the facility was designed to capture. So there was a disconnect there where it really wasn't economic for SAS Power to capture any more CO2 than they were being compensated for under the enhanced oil recovery agreement. So a few things that reduce the capacity over time. So this is a snapshot of the performance of the Boundary Dam Unit 3 facility over the 8 years of operation. You can see the black line is the capture percentage. So this is the capture percentage of every molecules of flue gas that has gone through the capture facility. So you can see that it is able to achieve basically the 90% design capture rate that it was planned to achieve. One of the issues is, again, the amount of flue gas that goes through the capture plant itself due to some of the economic factors that I've mentioned and some of the fouling and technical challenges. Not all of the flue gas goes through the Boundary Dam Unit 3 facility, but the flue gas that does, it gets captured at a rate of 90%. The gray line is the combined plant efficiency. So that's measuring the capture efficiency of the unit when compared to the full output of the power plant. So you can see it's in the 65% sort of range, and it's been climbing actually in the last number of years. 2021 was a bit of an anomaly where there was some non-carbon capture equipment related outage problems, typically primarily with the compressor. But 2022 has been quite a strong year, and actually in the 12-month period from February 1st, 2022 to January 31st, 2023, the plant has captured about 810,000 tons of CO2, which is the best 12-month period that it's had, and we're expecting that trend to continue. So we've built the Boundary Dam Unit 3 project. We've supported the ongoing operation and optimization activities of the BD3 project. What does that mean? How does that help you? How does that help anybody else that's looking at a carbon capture project? Well, our team is here essentially to apply the lessons learned and help people reduce their risk, lower their cost, and improve performance of their projects. These lessons learned from Boundary Dam Unit 3 are applicable to any post-combustion carbon capture and storage project across various industries, be it power generation, cement, mining, fertilizer, oil and gas, steel, or hydrogen production. And I'm probably missing a couple. Some of the key technical considerations that we like to share with people when we're talking to them about their projects are technology suitability and maturity. So what's the right technology for your application? Is it the liquid amine post-combustion capture process employed at Boundary Dam Unit 3? Is it some new technologies that are being developed, be it membrane processes, cryogenic processes, solid sorbent processes? There's a lot of work happening in terms of research for different types of technologies, different technologies that show promise for higher capture rates, lower energy requirements, those sorts of things. They're typically at the lower end of the technology readiness level scale. But if you've got time and you're not looking at a kind of a near-term in-service date, there's a lot of merit to keeping an eye on these technologies and considering them for your application. If you're in the mode of trying to get something done by 2030, you're likely looking at a more mature and commercially available technology. And today that's typically liquid amine post-combustion capture. But there are certainly options to look at, and that's something that we really try to keep abreast of here at the Knowledge Center is what's happening with the new technologies and how can we advise clients on what the right technology is for them based on their specific situation. Another key consideration that we talk to people about is flue gas characterization. And I mentioned this already. Flue gas is seen as a waste stream by most people today, and it's measured purely to satisfy essentially the regulator. What's going out my stack? What do people need to know about? And now it becomes an input to a sophisticated chemical process. You really need to understand it and do some very specialized testing to understand what's in it. And that's just a risk mitigation step to help ensure that you have reliable operation for years to come. Storage versus utilization. So utilization, there's a lot of research again in this space as carbon capture has really come to the forefront in the last couple of years in terms of the level of interest. What we see today is in terms of the scale and the magnitude of things that need to be done in the carbon capture space, there's really a volume mismatch between what's available on the utilization side versus the storage side. But we definitely encourage people to consider utilization, and we're really pleased that people are continuing to research utilization. I think in the short term there will be a combination. Any major, megaton sort of scale CCS project is going to need permanent storage sequestration, but there could be an opportunity to look at the utilization for a slipstream, and that's how the utilization technology will sort of gain traction and hopefully at some point get up to the same scale as what we have for storage today. I've mentioned thermal integration. This energy demand is always a key factor to consider when you're looking at a carbon capture and storage project. As I mentioned, we did a lot of work on this in the Boundary Dam Unit 3 project. We've worked with a number of clients looking at how to optimize their energy usage. Things like combined heat and power have shown to be quite attractive in terms of the business case in some jurisdictions. And lastly, it's the variation in understanding and sort of the ability to take on this new chemical type process or new capture process if it is one of the more emerging technologies. Typically, the industry is not used to that sort of technology, and there's a learning curve. There's a diversification of skill sets required, and it's important to understand that going into a project like this, that there's a lot of effort required to make your operational team ready to successfully operate and maintain this new equipment. So this graphic really shows a typical timeline for a carbon capture and storage project. It's maybe a little bit on the optimistic side, but we feel there's about a 1-year requirement to do kind of a high-level feasibility study. A FEED study could take about 2 years or so to get through all of the design aspects, the equipment selection, all the things required to make a final investment decision. You got a 3-year-ish construction, commissioning, performance testing. So about a 6-year undertaking to build a carbon capture and storage project. So it's a substantial undertaking, and it's important to make sure that you do it right. So what we've listed here is sort of some of the things that our team does to help support people that are considering carbon capture and storage projects. And as you would expect, the majority of the CCS projects in North America, around the world, are in this sort of orange pre-feasibility, feasibility, feed stage. And we've worked with a lot of people to do feasibility studies, providing owner support just to validate things that are coming out of their studies, or even managing feed studies altogether. We see once we get into the construction, commissioning, performance testing, there's some other services we can provide. And again, during the operation and optimization, which is probably 3 or 4 years down the road, we expect there are going to be some more relevant learnings from the Boundary Dam Unit 3 project and other projects that we supported that will be valuable to people when we get to that stage. So this is just an example of one of the projects that we're actively supporting. This is Heidelberg Materials CCS project in Edmonton, Alberta, Canada. So it's a cement facility, and one of the challenges that the cement industry has is about 2/3 of their emissions come from the actual calcination process that's involved in making cement. So even if they change fuels to, say from coal to natural gas or natural gas to hydrogen that doesn't produce CO2, they still have this emission just by virtue of their process. So they're an industry that really sees carbon capture and storage as a major part of their decarbonization efforts. So we worked with Heidelberg to complete an ERA-funded feasibility study in 2021. So this study was funded by Emissions Reduction Alberta. About 50% of the cost of the study was provided from the government of Alberta. We completed a combined heat and power analysis, which is shown to actually significantly improve the business case for this project. Rather than putting in an auxiliary boiler to produce the steam required to regenerate the amine, we use natural gas to produce steam that produces electricity first, and then the lower quality steam is used to actually regenerate the amine in the process. Significant financial improvement in terms on the business case. We're currently supporting a FEED study along with Heidelberg, essentially providing owner's engineer support. So we're not doing any of the detailed design. We're sort of a technical advisor to the owner to validate what they're hearing from their technology licensor and what their detailed engineering consultant is putting together for them. We also provide strategic advisory services, helping them navigate some of the different hurdles that are required to get a project like this to a final investment decision. So this is an example of some of the work that's happening in the CCS space, and we've seen this rapid acceleration in terms of the level of interest and the number of feasibility studies and FEED studies that are underway. So in the province of Alberta, I'd mentioned Emissions Reduction Alberta had funded the Heidelberg feasibility study. They actually have a funding program in place right now. It's called CCS Kickstart, and it's a $40 million investment on 11 projects that are looking at FEED studies for various versions of carbon capture and storage across primarily, I guess, 5 different industries. There are a number of projects in the oil and gas sector, typically the oil sands in Alberta. There's some chemicals and fertilizer projects, power generation projects. You can see 4 different ones that are underway, and some other industries, including cement with Lafarge, and a forestry project, bioenergy project. One of the things that the Knowledge Center is doing is we're actually part of the CCS Kickstart program, and we provide support, ERA-funded support to each of these 11 projects to ensure that they learn the lessons from the BD3 project and other projects that we've worked on to make sure that they can employ some of these real-world lessons learned and improve the outcomes, essentially, of their projects. So this is just a quick listing of some of the clients that we're currently supporting that are considering CCS on their facilities. Various stages of interest, from pre-feasibility phase to feed phase to even getting close to final investment decisions, and across all different industries. One of the things that's been quite apparent to us is the lessons learned from this BD3 project and subsequent projects are quite applicable to across various industries. There are things that different industries, different projects can all learn from each other. And that's one of the things we really try to do, is facilitate that knowledge sharing and incorporation of those lessons learned. So I've talked about the Boundary Dam Unit 3 project and how we can take some of those technical project-related lessons learned, and we can help improve the outcomes of projects across various industries. But how do we get there? How do we get these projects approved? How do we get people to companies to invest billions of dollars in these sorts of projects? We know that if the world has any chance of meeting net zero by 2050, a massive expansion of CCS is required. If you look at what the IEA publishes, global capacity of CCS must grow to more than 800 million tons per year by 2030. That's only 7 years away. And if you think about a 6-year lead time for a project, there's really not a whole lot of time to get to 800 million tons. Today in the world, there's about 40 megatons of CCS projects in service. So meeting this target will require more than 300 new projects to be developed by 2030. A tall order, no doubt. So with this type of activity required, there really needs to be strong collaboration between industry and government to move these projects forward. Essentially, almost without exception of maybe the forestry industry, these projects are drains on the balance sheets of corporations. They don't create any additional revenue. They're really just a cost line on your balance sheet, which needs to be supported by some sort of regulation, be it a production tax credit, an investment tax credit. Some sort of support is required for these projects to make sense, particularly in competitive environments. And really, what we're seeing now is there's kind of a race underway amongst nations to try to attract the massive capital investment of 300 plus $1 billion plus projects into their countries. And primarily the leader in this is the United States, with the 45Q regulation that's been in place for some time, recently being enhanced significantly by the Inflation Reduction Act. That seems to be the jurisdiction where most people are most multinational corporations looking to invest their dollars to reduce their emissions. Each country is developing their own blend of regulations. We like to call them carrots and sticks, the carrots that incent investment, the sticks that punish you if you don't invest. But regardless of the theme and how we get there, regardless of the mix and how we get to this point, one thing that we really support at the Knowledge Center is the need to share knowledge, the need to share lessons learned, the need to make sure that as billions of dollars of public money goes into these projects, all the information is gained is shared without any sort of retention, without any sort of strings attached, to make sure that projects around the world are as successful as possible. This kind of formal collaboration will help make the next generation of projects as successful as possible by learning from each other, ensuring taxpayers are getting the most value for their investment. This requirement can be seen as onerous for many companies, which is why it makes sense for dedicated and independent groups like the Knowledge Center to act as the curators of this valuable information. The Knowledge Center does have proposals underway to develop and manage CCS knowledge hubs for both the Canadian federal and Alberta's provincial governments, and we're in discussions with other partners to do the same in other countries. This role of being the knowledge sharing hub, knowledge sharing entity really aligns with our mandate and the work that we're trying to do to help improve the outcomes for CCS projects around the world. So I've talked about some of the technical issues with carbon capture projects and what can be done to sort of help to minimize those issues, what's required to help with the economic hurdles with getting some of these projects through to final investment decision. One of the last things I'll talk about is public engagement, public confidence. There's the growing interest in CCS has really led to more public questions and in some cases coordinated opposition to projects. This reinforces the need of building broad public understanding and confidence in CCS, reinforcing that it is actually a safe thing to do, and undertaking significant stakeholder engagement as early as possible in the development process for any project, in order to diffuse any of the legitimate questions that come forward and uncertainty in some of the local jurisdictions. Now, while the oil and gas industry has the most experience with these challenges, strategic stakeholder engagement and issues management on large infrastructure projects is uncharted territory for many other heavy emitting industries, and it's 100% necessary for any of these mega projects. It's important to apply the experience of building public trust and acceptability along with social license from successful projects such as BD3 or the Shell Quest CCS project in Canada, a number of oil and gas pipelines, the Petronova project in the United States, and many other energy and resource projects, if they are to be successfully built. We need to learn from what's been done to make those projects successful. By acting as a neutral and trustworthy advisors, we're here to help our clients successfully navigate the myriad of technical, economic, policy, and stakeholder issues that accompany the development of major CCS projects worldwide. Thanks for your time, and I'm really looking forward to the Q&A session where I don't have to just talk to my camera. Thanks a lot.